Imagine for a moment the most violent explosion you could possibly conceive, something so immensely powerful it outshines entire galaxies in a fraction of a second. Now picture that happening billions of light years away, so far in space and time that the light reaching us now began its journey when the universe itself was still young. These are gamma-ray bursts, the most energetic event since the Big Bang, cosmic fireworks on a scale that defies human imagination. In the vast emptiness of space, they appear without warning, flicker for mere moments, and then vanish, leaving behind only questions and a trail of high-energy radiation that astronomers race to decode. What if I told you that these fleeting flashes of light are not just spectacular shows, but cosmic messengers carrying secrets from the farthest edges of the observable universe? The most distant gamma-ray bursts allow us to peer back through time, offering glimpses into the early cosmos, the formation of the first stars, and perhaps even the very conditions that made life possible. They challenge our understanding of physics, time, and our place in the universe. And in this video, we're going to explore 30 astonishing facts about these phenomena, each one more mind-bending than the last. From how they form to what they tell us about the fate of the cosmos, we're about to go on a journey that stretches across space and time. This isn't just a story about faraway explosions. It's about human curiosity, our relentless drive to understand the unknown, and the profound connections between the universe's grandest events and our own existence. So settle in, open your mind, and get ready to explore the farthest, most mysterious reaches of space through the lens of gamma-ray bursts. By the end of this video, you won't just see the night sky the same way again. You'll understand it differently, with a sense of awe only the cosmos can inspire. At its core, a gamma-ray burst is exactly what its name implies: a sudden, intense burst of gamma-ray light. But that simple definition barely scratches the surface of its true nature. To truly grasp what this means, you first need to understand gamma rays themselves. They are the most energetic form of light in the universe, far beyond what our eyes can see or even what an X-ray machine produces. This light carries so much power that a single photon of gamma radiation can contain millions of times more energy than a particle of visible light. Now, imagine an event so cataclysmic that it unleashes a tsunami of these gamma-ray photons all at once. In a matter of seconds, a single gamma-ray burst can release more energy than our Sun will emit over its entire 10 billion-year lifespan. This isn't just a flash, it's the single most violent, explosive event known to occur in the cosmos since the primordial fire of the Big Bang itself. It is the ultimate cosmic tantrum, a brief but unimaginably powerful release of energy that, for its fleeting duration, outshines every star, every quasar, and every other object in the entire gamma-ray sky combined. What makes these events so fascinating and so challenging to study is their fleeting nature. They appear at random anywhere in the sky without any warning. The initial burst of gamma rays typically lasts from a few milliseconds to several minutes. In the grand, slow-moving timeline of the universe, which operates over billions of years, these bursts are over in the blink of a cosmic eye. They vanish almost as quickly as they appear, leaving astronomers with only a rapidly fading afterglow to study. This incredible combination of raw power and brevity is what makes them one of modern astronomy's greatest puzzles and most thrilling frontiers. But with such immense power condensed into such a short event, astronomers quickly realized they weren't all the same. To truly understand what causes these cosmic explosions, a crucial distinction had to be made. It turns out that timing is everything. By simply measuring how long the initial burst of gamma rays lasts, scientists can categorize them into two fundamentally different types, each with its own dramatic origin story. The first category is known as long-duration gamma-ray bursts. These events last for more than 2 seconds, and many can go on for several minutes. While that still seems incredibly brief to us in the world of GRBs, that's a long, drawn-out affair. This extended timescale is a vital clue pointing directly to their cataclysmic source. Long GRBs are now understood to be the death cries of the most massive stars in the universe. When a star many times heavier than our Sun exhausts its nuclear fuel, its core collapses not into a neutron star but directly into a black hole. This isn't a quiet fading away, it's a violent, asymmetrical implosion. As the star's outer layers come crashing down, some of the material is funneled into two incredibly powerful jets that shoot out from the poles at nearly the speed of light. If one of those jets happens to be pointed directly at Earth, we see it as a long gamma-ray burst. These events are almost always accompanied by a supernova explosion, a spectacular stellar funeral that marks the birth of a new black hole. They are the universe's way of announcing the end of a giant. On the opposite end of the spectrum are the short-duration gamma-ray bursts. These are the blink and you'll miss them events, lasting less than 2 seconds and often only a few hundred milliseconds. Their incredible brevity suggested a completely different, even more extreme engine was at work. For decades, their origin was one of astronomy's biggest mysteries, until a monumental discovery in 2017 provided the answer. That year, astronomers detected a short GRB and, for the first time, paired it with ripples in spacetime itself, gravitational waves caused by the collision of two ultra-dense neutron stars. This confirmed the leading theory: short GRBs are the result of a binary neutron star merger. Picture two city-sized stellar corpses, each with a mass greater than our Sun, locked in a final, fatal dance. They spiral inward over millennia until they finally smash together, creating either a new, heavier neutron star or a black hole almost instantaneously. This merger also launches jets of material and radiation, producing that incredibly short, unimaginably intense flash of gamma rays. Unlike their longer cousins, these events are not accompanied by a supernova. They are the final, silent end of stars that have already died. But before these bursts could be understood, they first had to be found, and their discovery is a story of Cold War intrigue and scientific serendipity. In the 1960s, at the height of the nuclear arms race, the United States launched a series of top-secret satellites known as Vela. Their singular mission was not to explore the cosmos, but to watch for violations of the Nuclear Test Ban Treaty. The Velas were essentially nuclear watchdogs in space, equipped with X-ray, gamma-ray, and neutron detectors designed to spot the unmistakable signature of an atomic detonation in the Earth's atmosphere or in the void beyond. For years, these satellites dutifully monitored the skies. Then, on July 2, 1967, the sensors on board Vela 4 and Vela 3 registered something extraordinary. They detected a sudden, massive spike of gamma radiation. It didn't match the profile of a nuclear bomb. It was too powerful, too brief, and most puzzling of all, it didn't come from the direction of Earth. The signal had originated somewhere out in deep space. The scientists analyzing the data, led by Ray Klebisadel at the Los Alamos National Laboratory, were baffled. What could possibly produce such an immense, fleeting burst of energy? Over the next few years, more of these mysterious events were detected, always from random directions in the sky. The data was so strange and so unexpected that the team spent years verifying their instruments and their findings before they were confident enough to publish. The initial 1973 paper cautiously announced the discovery of brief, intense bursts of cosmic gamma rays, and with that, one of the greatest astronomical mysteries of the 20th century was born. For nearly a decade, the true nature of these bursts remained completely unknown. The biggest puzzle was their distribution across the sky. They appeared to come from everywhere equally, with no concentration in the plane of our Milky Way galaxy. This was a massive clue. If these events were originating from within our own galaxy, you would expect to see them clustered along the galactic disk where most stars reside. Their isotropic or uniform distribution strongly suggested they were coming from far beyond the Milky Way, from the vast distances of intergalactic space. This realization was both thrilling and deeply troubling. If these bursts were truly extragalactic, the energy required to make them visible across such immense distances was staggering, completely defying any known physics or astrophysical process at the time. The scientific community was split into two camps, one believing they were relatively local events within our galactic neighborhood, and the other convinced they were cosmological monsters from the edge of the observable universe. The debate raged for decades, a classic scientific detective story with the entire cosmos as the crime scene. The mystery of where these bursts came from was finally cracked, not with a single telescope on the ground, but with a new generation of agile observatories in space, specifically designed to catch these cosmic fugitives in the act. For decades, the greatest challenge was their unpredictability and speed. By the time a ground-based telescope could be manually pointed at the coordinates of a burst, the brilliant afterglow had often faded into nothingness, leaving astronomers with very little to study. What was desperately needed was a rapid response mission, a cosmic police force that could instantly swing into action the moment a GRB was detected. This need led to one of the most successful astronomical missions in history, NASA Neil Gehrels Swift Observatory, named in honor of its late mission scientist. Launched in 2004, Swift was a revolutionary concept. It wasn't just a single telescope, it was a multi-wavelength detective. Its first instrument, the Burst Alert Telescope, or BAT, constantly scans over a sixth of the sky at any given moment, waiting for a gamma-ray burst to trigger its sensors. The moment it detects one, within mere seconds, the entire spacecraft autonomously and swiftly slews or turns to bring its other two telescopes to bear on the exact location. The X-ray telescope and the ultraviolet/optical telescope then begin observing the fading afterglow, pinpointing its position with incredible accuracy and relaying those coordinates to observatories all over the world within minutes, sometimes even seconds. This automated rapid response system transformed the field from one of lucky catches to one of guaranteed science. For the first time, astronomers could be certain they would get detailed, multi-wavelength data on a burst almost from the very moment it happened. While Swift was the rapid responder, another mission launched to provide a different, equally critical perspective. The Fermi Gamma Ray Space Telescope, launched in 2008, carries two main instruments. The Large Area Telescope surveys the entire sky every 3 hours, building a deep map of the high-energy universe. But its partner instrument, the Gamma Ray Burst Monitor, is specifically tuned to catch the brilliant flashes of GRBs. Fermi's unique strength lies in its enormous energy range. It can detect photons from a few thousand electron volts all the way up to an astonishing 300 billion electron volts. To put that in perspective, that's energy levels hundreds of millions of times greater than that of visible light. This capability allowed Fermi to make a landmark discovery. Some gamma-ray bursts are not just bright in gamma rays, they are also sources of ultra-high-energy gamma rays, a finding that challenged existing theories about the particle acceleration happening within the relativistic jets. Together, Swift and Fermi have formed an unbeatable team, a dynamic duo in the hunt for these explosions. Swift provides the precise location and the detailed early-time light curves across multiple wavelengths, while Fermi provides the breathtaking, broad-spectrum energy profile. This partnership has been the engine behind the study of thousands of gamma-ray bursts. Their data has been instrumental in confirming the connection between long bursts and supernova, and it was Fermi, alongside gravitational wave observatories, that played a key role in confirming that short bursts originate from neutron star mergers. By delivering precise coordinates to ground-based telescopes within moments of a burst, they have enabled measurements of the redshifts of these events, confirming their incredible distances and allowing us to use them as probes of the early universe. Their contributions have moved GRB science from a field of mystery and debate to one of concrete discovery and profound cosmological insight. And the key to unlocking that distance, to truly understanding how far back in time we are looking, lies in a phenomenon known as redshift, represented by the letter Z. This single measurement is the most important tool in a cosmologist's toolbox, the universal ruler for the cosmos. The concept hinges on a fundamental property of light and the very nature of the expanding universe. Think of the sound of a passing ambulance siren. As it moves away from you, the sound waves are stretched, causing the pitch to drop. This is the Doppler effect, and light behaves in a remarkably similar way. When an object in space is moving away from us, the light waves it emits are stretched out along their journey to our telescopes. Because light is a wave, this stretching physically shifts it toward the red end of the electromagnetic spectrum. The faster an object is moving away, the more its light is redshifted. But with gamma-ray bursts and other incredibly distant objects, it's not just about the object's own motion through space. It's about the expansion of space itself. The universe is stretching, and as light travels across this vast, expanding fabric over billions of years, the space it travels through stretches, which in turn stretches the light waves. The longer the journey, the more stretching occurs, and the greater the redshift we measure. This is where the Z value comes in. It's not just a number, it's a direct readout of cosmic history. A higher Z value means the light has been stretched more, which means it has traveled a greater distance across more expanding space, which also means we are seeing that object at a much earlier epoch in the universe's life. For relatively nearby objects, the math is straightforward. A galaxy with a redshift of Z equals 0.1 is seen as it was about 1.3 billion years ago. But for the most distant gamma-ray bursts, the numbers become almost philosophical. A burst with a redshift of Z equals 6 means we are witnessing an event that occurred when the universe was less than 1 billion years old. A burst with a staggering Z value of 9.4, like one record holder, shines from a time when the cosmos was a mere 500 million years old, a mere infant. This transformative measurement allows astronomers to do more than just place these bursts on a timeline. It lets them use the bursts as probes. By analyzing the specific signature of the light after it has been redshifted, scientists can dissect the composition of the material the burst light passed through on its multi-billion-year journey to Earth. They can detect the faint fingerprints of primordial gas clouds and early galaxies, mapping the structure of the infant universe in a way that would be impossible with any other cosmic event. The incredible luminosity of a gamma-ray burst acts like a brilliant flashlight beam shining through the cosmic fog, and redshift is the tool that tells us exactly how far away that flashlight was turned on. But to truly appreciate the scale of these cosmic distances, we need to meet the current record holder, an event that pushes the limits of our observatories and our imagination. Known as GRB 090429b, this burst was detected by the SWIFT satellite in April 2009. Its initial detection was impressive but not immediately record-breaking. It was the meticulous, years-long forensic work that followed which revealed its true, staggering nature. The afterglow from this burst was so faint and faded so quickly that astronomers couldn't pin down its exact redshift right away. It took a combination of data from swift and powerful ground-based telescopes like the Gemini Observatory in Hawaii to analyze the faint whisper of light that remained. They weren't looking for specific emission lines which had faded beyond detection, but instead relied on a technique called photometric redshift, comparing the brightness of the afterglow across different filters to estimate its distance. The results pointed to a redshift of approximately Z equals 9.4. That number, Z equals 9.4, is far more than a statistic. It's a timestamp from the dawn of time. It means the light from this cataclysm has been racing across the expanding universe for over 13 billion years before finally triggering our sensors. We are witnessing this explosion not as it is now, but as it was when the universe was in its extreme infancy, a mere 500 million years old. To put that into perspective, our solar system wouldn't even begin to form for another 8 billion years. This burst occurred during the cosmic epoch known as reionization, when the first stars and galaxies were just starting to ignite, burning away the primordial fog of hydrogen that filled the empty cosmos. It is a direct glimpse into the era of the very first generations of stars, a period we often call the cosmic dark ages because it is so challenging to observe. What makes GRB 090429b so special is that it acts as a brilliant beacon shining through that ancient fog. The fact that a gamma-ray burst could occur so early in the universe's history tells us that the ingredients for these monstrous explosions, very massive stars, and the conditions to form them were already in place astonishingly quickly after the Big Bang. This places powerful constraints on how quickly the first stars and galaxies could assemble. The universe worked fast, and GRB 090429b is the proof, a single, fleeting flash of evidence that the early cosmos was already a dynamic and violently creative place, capable of producing stellar titans and their spectacular deaths at a time when the universe was less than 5% of its current age. It stands as a monument to how far our technology and ingenuity have come, allowing us to reach back and almost touch the beginning of everything. But while GRB 090429b provided a breathtaking photometric estimate, the world of science thrives on certainty. For a discovery of this magnitude to move from a compelling estimate to an undisputed fact, it required spectroscopic confirmation, a precise measurement that could only be achieved by dissecting the light of the burst's afterglow into its individual wavelengths to find the unmistakable fingerprint of redshift. This crucial step arrived just weeks later with another monumental event, one that would earn the official title of the most distant gamma-ray burst ever confirmed. In the pre-dawn hours of April 23, 2009, the Swift Satellite's Burst Alert Telescope was triggered by a surge of gamma rays. This burst, catalogued as GRB 090423, lasted for a relatively long 10 seconds, immediately marking it as the death cry of a massive star. Swift swiftly autonomously slewed, and its X-ray telescope successfully locked onto a rapidly fading X-ray afterglow, providing a precise celestial coordinate for astronomers around the world to target. The race was on. The afterglow was incredibly faint, a dimming ember from the edge of time, and it was visible only from the largest telescopes on Earth. Just over an hour after the initial alert, a team led by Niall Tanvir of the University of Leicester in the United Kingdom pointed the powerful United Kingdom Infrared Telescope, or UKIRT, in Hawaii toward the spot. They were hunting for the afterglow in infrared light, knowing that the extreme redshift would have stretched any visible light far into the infrared part of the spectrum. They found it a faint pinprick of infrared light where nothing had been before. The next night, an even more critical observation was made using one of the twin Gemini North telescopes, also in Hawaii. The team used the Gemini near-infrared spectrograph to capture the light of the fading afterglow and break it apart into a spectrum, a rainbow of infrared light that held the definitive secret to its distance. The resulting data revealed a featureless, nearly flat spectrum, which was exactly what they expected to see. The brilliant light from the burst had traveled so far that the characteristic spectral lines, the fingerprints of specific elements, had been redshifted completely out of the range of the instrument. However, there was one critical feature they could detect: the Lyman alpha break. This is a fundamental phenomenon in extragalactic astronomy. Intergalactic hydrogen gas efficiently absorbs all light at wavelengths shorter than a specific threshold known as the Lyman alpha line. In the spectrum of GRB 090423, this absorption edge was clearly detected, but it was located not in the ultraviolet where it normally is, but deep in the infrared. The precise location of this break in the spectrum allowed astronomers to calculate the redshift with stunning precision. Z equals 8.2. This number cemented its place in history. It meant the progenitor star exploded when the universe was just 630 million years old, a mere 4% of its current age. This spectroscopic confirmation was the definitive proof the astronomical community needed. It wasn't an estimate, it was a direct measurement. GRB 090423 wasn't just a distant flash. It was a message from the era of the first stars, proving conclusively that the early universe was not a quiet, placid place. It was already a dynamic and violent cosmos, capable of forming colossal stars and witnessing their spectacular deaths in cataclysmic gamma-ray bursts within the first billion years of existence. This single measurement transformed our understanding of cosmic evolution, demonstrating that the first generations of stars included true behemoths, and that the universe got down to the business of creation and destruction almost immediately after the cosmic dawn. To comprehend the staggering energy of a gamma-ray burst, we first need a tangible frame of reference, and our own sun provides the perfect yardstick. Our sun is a cosmic powerhouse. Every second, it fuses approximately 600 million tons of hydrogen into helium, releasing an almost incomprehensible amount of energy in the process. Over the course of its entire 10 billion-year lifespan, this steady, reliable furnace will radiate a monumental total of about 1 × 10⁻³ power joules of energy. This is a 1 followed by 34 zeros. This is the energy that has nurtured life on Earth for billions of years and will continue to do so for billions more. A typical long-duration gamma-ray burst, the kind associated with the death of a massive star, unleashes this same colossal amount of energy, the sun's entire lifetime output, but it does so in a matter of seconds, not billions of years. The key, however, is in the details of how that energy is released. The total energy of the burst, known as its isotropic equivalent energy, is calculated under the assumption that the explosion radiates its power equally in all directions. In reality, we now know the energy is focused into 2 incredibly narrow, blisteringly hot jets of plasma and radiation that travel at over 99.99% the speed of light. This beaming effect is the secret behind their mind-bending luminosity. All of that cataclysmic force is concentrated into a pair of laser-like beams. If one of those beams is pointed directly at Earth, we see the full, unfiltered fury of the event, making it appear impossibly bright. Now, apply this understanding to the most distant bursts we've been discussing. Their light has traveled for over 13 billion years to reach us. The expansion of the universe has stretched their light waves and diluted their energy, yet they still trigger our satellites with incredible force. To be visible across such a vast, expanding gulf of space, the intrinsic energy of these events must have been almost beyond calculation. For a burst at a redshift of Z equals 9, its luminosity distance, a measure that accounts for the universe's expansion, is truly astronomical. The energy we receive is only a tiny, faded fraction of what was originally emitted. To appear as bright as it does to our instruments, the burst must have been, for its brief duration, millions of times brighter than the combined light of every star in a galaxy like our Milky Way. This extreme luminosity makes these distant events the ultimate cosmic lighthouses. Their beams cutting across the observable universe, they briefly become the single brightest objects in existence, outshining quasars and active galactic nuclei. The power generated in the heart of a collapsing stellar core, channeled through relativistic jets, represents the most efficient engine for converting mass into energy in the known universe, rivaled only by the Big Bang itself. It is a scale of power that human technology cannot even approach and that astrophysics is still striving to fully model. These are not merely stellar explosions. They are the universe operating at its absolute physical limits, demonstrating a raw, violent potency that defines the most energetic epochs of cosmic history. This incredible brightness is what transforms a gamma ray burst from a catastrophic stellar death into one of astronomy's most valuable tools. Think of the early universe not as the star-filled tapestry we see today, but as a vast, opaque fog. For hundreds of millions of years after the Big Bang, the cosmos was filled with a dense soup of neutral hydrogen gas that absorbed most light, shrouding everything in what we call the cosmic dark ages. This period is incredibly difficult to study because the very first stars and proto-galaxies were faint and hidden behind this veil. We need a brilliant, piercing light to see through that fog, and nothing shines brighter than a gamma-ray burst. When one of these explosions occurred in that primordial era, it acted like a cosmic flashlight. Its intense beam of radiation, particularly in ultraviolet and X-ray light, shot out in opposite directions. As this light traveled through the ancient intergalactic medium, it didn't just illuminate the path, it interacted with it. The neutral hydrogen atoms along the beam's path absorbed specific, characteristic wavelengths of light. By the time that faint afterglow finally reaches our telescopes billions of years later, its spectrum, the detailed breakdown of its light, contains the absorption fingerprints of every cloud of gas it passed through. Astronomers use a technique called absorption spectroscopy to read this cosmic barcode. They don't see the gas clouds themselves. Instead, they see the shadows they cast on the GRBs' light. Each dark line in the spectrum corresponds to a specific element at a specific redshift, allowing scientists to map the distribution, temperature, density, and chemical composition of the matter that existed between the burst and us. A GRB at a redshift of 8 doesn't just tell us about the explosion itself. It provides a brilliantly lit core sample of the universe's condition when it was only 600 million years old. We can analyze the tenuous gas in the vast voids between the earliest galaxies and study the environments right around the progenitor star itself. This turns a single, fleeting event into a multi-purpose observatory, granting us a direct line of sight back to an epoch that is otherwise almost completely inaccessible. These most distant bursts are our only chance to empirically study the structure of the universe during its first formative billion years, making them invaluable probes of cosmic evolution. This journey of light from the most distant gamma-ray bursts does more than just mark a distance. It carries an encoded history of the entire path it has traveled, acting as a core sample through billions of years of cosmic evolution. One of the most critical eras it passes through is known as the epoch of reionization, a transformative period that fundamentally changed the nature of the universe. To understand this, we need to rewind to a time just after the Big Bang. The early universe was a hot, dense plasma of particles, but as it expanded and cooled, protons and electrons combined to form neutral hydrogen atoms. This event, called recombination, left the cosmos dark and opaque, a vast, unlit fog of neutral gas that stretched everywhere. This was the beginning of the cosmic dark ages, a time when no stars or galaxies yet shone to pierce the gloom. The epoch of reionization marks the end of those dark ages. It was the universe's great awakening, a several hundred million-year transition when the first luminous objects, the earliest stars and galaxies, switched on. Their intense ultraviolet radiation began to bombard the surrounding neutral hydrogen, stripping electrons from their atoms in a process called ionization. Think of it like a frost melting slowly under a rising sun. Patches of clear, transparent space began to appear in the cosmic fog as these bubbles of ionized gas grew and eventually merged. This was not a gentle process. It was a dramatic upheaval that altered the very fabric of intergalactic space, making it transparent to light and allowing the universe to become the star-filled vista we observe today. Studying this epoch is incredibly difficult because the first galaxies are exceedingly faint, and the neutral hydrogen itself is nearly impossible to see directly. This is where the most distant gamma-ray bursts become absolutely indispensable. a GRB that explodes during or just after reionization, like GRB 090423 at Z equals 8.2, sends a brilliant flash of light racing through this partially ionized medium. The light from its afterglow, especially in the ultraviolet part of the spectrum, is systematically absorbed by any remaining patches of neutral hydrogen it encounters along its path. This creates a unique and telling signature in the burst spectrum known as the Lyman alpha forest, but on a colossal scale. For a very high redshift burst, astronomers don't see a forest of individual lines, they see a complete Gunn-Peterson trough. This is a broad, smooth swath of absorption where virtually all the light at wavelengths shorter than the Lyman alpha line has been eaten away by the pervasive neutral hydrogen, a clear sign that the light traveled through a universe that was not yet fully clear. By analyzing the precise shape and depth of this trough in the spectrum of a distant GRB afterglow, scientists can determine the fraction of hydrogen that was still neutral at that specific time in cosmic history. It allows them to map the progress of reionization not as a single, simple event, but as a gradual, uneven process. Did reionization happen quickly or slowly? Were the first stars the primary drivers, or were early quasars also major contributors? The light from these gamma-ray bursts holds the answers. Each distant burst acts as a single, precisely dated probe, and by collecting data from several of them at different redshifts, astronomers can piece together a timeline of this universal phase change. They are using the most violent explosions in the cosmos as backlights to study the delicate process of how the first light pierced the darkness, transforming the universe from an opaque fog into the transparent, star-filled expanse we call home. But for all their raw power, the initial gamma-ray flash is just the opening act, a spectacular but frustratingly brief prelude. If that were the entire show, astronomers would be left with little more than a set of cosmic coordinates and a profound sense of mystery. The true scientific goldmine, the key that unlocks the secrets of these explosions, is what comes next, the afterglow. Imagine the most brilliant firework you've ever seen exploding in the sky. The initial burst is blinding, but it's the lingering, fading embers that dance and swirl against the night that truly captivate you. In the same way, a gamma-ray burst's initial flash is over in seconds, but its afterglow can persist for days, weeks, or even months, shining across the entire electromagnetic spectrum and telling the detailed story of the explosion long after the main event has concluded. This remarkable phenomenon begins the moment the relativistic jets responsible for the gamma rays plow into the surrounding interstellar medium. This isn't empty space, it's filled with tenuous gas and dust. When the jet slams into this material at nearly the speed of light, it creates a colossal shock wave like a cosmic sonic boom. This shock wave violently energizes the particles in its path, causing them to radiate energy as they decelerate. This radiation is the afterglow, and it starts at the highest energies in X-rays before progressively cascading down through ultraviolet, visible light, infrared, and finally into radio waves. This multi-wavelength light show is our window into the physics of the burst, providing a wealth of information that the initial flash simply cannot. The evolution of this light is an intricate and beautiful dance of physics. In the first few minutes after the burst, the afterglow is typically brightest in X-rays, which is why satellites like SWIFT are so crucial for immediate follow-up. Over the course of several hours, the peak of the emission shifts downward in energy, becoming brightest in visible light. This is the brief window when large ground-based optical telescopes can swoop in to capture a spectrum, which is how we measure the all-important redshift. Days later, as the visible light fades, the afterglow often experiences a resurgence in the infrared and radio bands. This radio afterglow can be particularly long-lived, sometimes detectable for months. Each wavelength band tells a different part of the story. The X-rays reveal the most energetic processes happening within the shock front. The optical light gives us the distance and the broad geometry. The radio emission is especially valuable because it allows us to peer through any obscuring dust around the burst and can even be used to measure the total energy and the precise geometry of the explosion through a technique called very long baseline interferometry, which can actually resolve the expanding fireball. Without this sustained multi-wavelength afterglow, the field of gamma-ray burst astronomy would simply not exist in its current form. The initial burst from a distant event like GRB 090423 is detected, but its location might only be narrowed down to an area of the sky the size of your hand held at arm's length. The afterglow provides the precise arcsecond level coordinates required to point the world's most powerful telescopes at the exact spot. It is the address written on the envelope, allowing us to deliver our instruments to the right doorstep in the cosmos. It is the fading ember that guides us to the cosmic campfire, ensuring that a fleeting moment of violence becomes a lasting source of discovery. This leads us to one of the most profound implications of these distant explosions, the very real possibility that we are witnessing the death cries of the universe's very first stars. To understand why this is so revolutionary, we need to meet population 3 stars. Astronomers categorize stars into populations based on their metallicity, a term that sounds technical but simply means the fraction of elements heavier than hydrogen and helium within them. Our Sun is a population 1 star, rich in metals like carbon, oxygen, and iron, the forged remains of countless generations of stars that lived and died before it. Population 3 stars are the hypothetical, pristine originals. They formed from the primordial soup of gas left over from the Big Bang, which contained only hydrogen, helium, and a trace amount of lithium. Nothing else, without heavier elements to help cool the gas clouds and fragment them. The physics of their formation was completely different. Theories and sophisticated computer simulations suggest these first stars weren't just large, they were true cosmic behemoths, often reaching masses hundreds of times that of our Sun. They would have burned at ferociously high temperatures, with lives that were spectacularly brilliant and brutally short. Instead of shining steadily for billions of years, a population 3 star would have consumed its nuclear fuel in a frenzied few million years before meeting a violent end. Their death is where gamma-ray bursts enter the picture. The current model for long GRBs requires a massive, rapidly rotating star with a core that collapses directly into a black hole. Population 3 stars are perfect candidates. Their immense mass provides the fuel for a cataclysm, and their pure hydrogen-helium composition means they likely lose very little mass through stellar winds during their lives. This is crucial because it allows the star to retain its angular momentum, its spin, all the way to the end. A massive, fast-spinning core is the essential ingredient for launching the relativistic jets that create a gamma-ray burst. Therefore, the death of one of these first stars wouldn't just be a supernova. It would be a hypernova, an explosion of such staggering power that it could easily produce a gamma-ray burst visible across the universe. When we detect a gamma-ray burst at a redshift beyond 8, we are looking back to a time when the universe was less than 650 million years old. This was deep within the era when the first stars were forming and dying. The existence of a GRB at this epoch is powerful, albeit indirect, evidence that these mythical population 3 stars were not just theoretical. They were real, and some of them died in the most extreme way possible. A distant GRB is a likely candidate for being the smoking gun, the telltale sign of a population Roman 3 star's final act. While we haven't yet captured the specific spectral signature of a pair instability supernova, a theorized fate for the very largest population 3 stars, from a GRB afterglow, the mere existence of these explosions in the early universe strongly suggests the first stellar generation included the kind of massive, unstable giants that could power them. Each distant burst is a potential message in a bottle from the dawn of time, carrying within its fading light the story of the first stars to ever shine. Detecting these whispers from the cosmic dawn is one of the most formidable challenges in modern astronomy. The very expansion of the universe that lets us peer back in time also works against our efforts to see these events clearly. A gamma-ray burst that was once brilliant enough to outshine galaxies has its light stretched and diluted over its billion-year journey. The incredible distances involved mean that by the time this faint echo of a cataclysm finally arrives at our doorstep, it is astronomically faint. The visible light and ultraviolet radiation that make up the bulk of the afterglows emission have been stretched far beyond what the human eye can perceive, shifted deep into the infrared part of the electromagnetic spectrum. This presents a monumental observational hurdle, as the Earth's atmosphere itself is a major obstacle. It glows brightly in the infrared and blocks most of these signals from reaching the ground, making faint, high redshift afterglows nearly impossible to detect with even the largest terrestrial telescopes. This is where a new generation of space-based observatories enters the story, instruments designed specifically to see the cold, faint universe. For years, NASA's Spitzer Space Telescope provided valuable infrared eyes, but the true game-changer is the James Webb Space Telescope. With its massive gold-coated beryllium mirror spanning 6.5 meters and its suite of instruments permanently cooled to operating temperatures just a few tens of degrees above absolute zero, Webb is the most powerful infrared observatory ever deployed. It was built with a key goal in mind: to peer back into the era of the first stars and galaxies, making it the perfect instrument to hunt for the most distant gamma-ray bursts. Its unparalleled sensitivity allows it to see the faint infrared afterglow of a burst that will be completely invisible to other telescopes, and its spectroscopic capabilities are powerful enough to dissect that faint light and measure its redshift with precision, even from the edge of the observable universe. The process is a race against time. When a satellite like SWIFT detects a potential high redshift candidate, an alert is sent out instantly to observatories around the world and in space. The James Webb Space Telescope, while not an agile rapid response mission like SWIFT, can be scheduled for target of opportunity observations. Astronomers must act swiftly to submit a compelling proposal to interrupt Webb's carefully planned schedule and point its colossal mirror at the fading afterglow. If approved, Webb gets to work using instruments like NIR-CAM to image the field and NIR-SPEC to obtain a critical spectrum. This data is what transforms a candidate into a confirmed record breaker, providing the definitive evidence that we are truly witnessing the death of a star from the universe's infancy. Without this infrared capability, the most distant and scientifically valuable bursts would simply remain unseen, their secrets lost to the vast, expanding darkness. But to see the very first of these stellar deaths, we need to push our observational capabilities to the absolute limit, and sometimes we get a helping hand from the universe itself through a phenomenon predicted by Einstein's theory of general relativity: gravitational lensing. This extraordinary effect turns the fabric of spacetime into the most powerful telescope imaginable. According to Einstein, massive objects don't just sit in space, they warp the very spacetime around them. Think of spacetime as a taut, flexible rubber sheet. Placing a heavy bowling ball in the center creates a deep dimple. Now, if you roll a marble across that sheet, its path will curve as it passes near the bowling ball. Light behaves in exactly the same way. Even though it has no mass, a beam of light will follow the curved path created by a massive object's gravitational well. When this happens on a cosmic scale, the results are breathtaking. A massive foreground object, like a galaxy or an entire cluster of galaxies, can bend and distort the light from a far more distant object directly behind it. This doesn't just bend the light, it can magnify it, amplify it, and even create multiple images of the same background object, like a funhouse mirror on a galactic scale. For astronomers, this is like being gifted a natural telescope of unimaginable power. It allows us to see objects that are so distant and intrinsically faint that they would be completely undetectable by any human-made observatory, no matter how advanced. In the hunt for the most distant gamma-ray bursts, gravitational lensing offers a potential window into realms otherwise beyond our reach. The ideal scenario involves a massive galaxy cluster situated perfectly between us and an incredibly high redshift GRB. As the faint light from the burst travels toward us, it passes through the immense gravitational field of the cluster. This cosmic lens can focus that light, brightening the afterglow by a factor of 10, 20, or even more. This amplification is the difference between seeing nothing and seeing everything. A burst that would have been a mere blip on a detector, too faint for any spectroscopic follow-up, could suddenly become bright enough for the James Webb Space Telescope to analyze in exquisite detail. Beyond simple magnification, lensing can also provide a spectacular visual distortion. Instead of a single point of light, we might see multiple images of the same afterglow arranged in a circular arc or cross-like pattern around the lensing cluster, a telltale sign known as an Einstein ring. Observing this not only confirms the lensing effect but also provides cosmologists with valuable data. By studying the geometry of the lensed images, scientists can map the distribution of both normal and dark matter within the foreground cluster, making a single GRB observation a two-for-one deal, a detailed probe of the early universe and a tool for weighing the invisible matter that dominates our cosmos. While a definitively lensed gamma-ray burst from the extreme early universe remains a holy grail that astronomers are actively searching for, the principle is firmly established by the lensing of other distant objects like quasars and galaxies. The potential is enormous. A gravitationally lensed GRB could act as a supercharged probe, its magnified light allowing for an unprecedented analysis of the gas conditions in the direct environment of one of the first stars to die in the universe. It would offer a level of detail about the progenitor star and its surroundings that would otherwise be impossible to obtain, effectively using the gravity of a massive cluster as a free boost to our observational power, bringing the cosmic dawn into sharper focus than ever before. This brings us to one of the most profound and chilling facts about these cosmic detonations. They are almost certainly the birth cries of newborn black holes. The prevailing model that astronomers have painstakingly built over decades points to a single, inescapable conclusion. A gamma-ray burst is the universe's way of announcing that a point of no return has been crossed and a new black hole has just come into existence. The specific circumstances of that birth determine everything about the burst we observe, neatly dividing them into the two distinct categories of long and short duration. For a long gamma-ray burst, the story begins with the death of a true stellar titan, a star at least 40 times more massive than our Sun. For millions of years, this star has maintained a fragile balance, the outward pressure from its internal nuclear fusion fighting a constant battle against the immense inward pull of its own gravity. But when it finally exhausts its nuclear fuel, that balance shatters in an instant. The star's core, no longer supported by fusion energy, catastrophically collapses under its own weight. This isn't a gentle shrinking, it's a free-fall collapse that takes less than a second. If the core is massive enough, perhaps over 2 or 3 solar masses, not even the formation of a neutron star can stop it. The collapse continues, crushing matter into a singularity and forming a black hole right at the heart of the dying star. But the story doesn't end there. This is where the gamma-ray burst itself is born. Not all of the star's material falls directly into the newborn black hole. A significant amount forms a vast, swirling, superheated disk of debris and accretion disk orbiting just beyond the event horizon. The physics in this region are among the most extreme in the universe. Intense magnetic fields are wound up to incredible strengths by the disk's rapid rotation, and friction within the disk itself heats it to temperatures of billions of degrees. This chaotic maelstrom of matter, energy, and magnetism acts like a colossal engine. along the black hole's rotational axis where resistance is lowest, this engine finds its exhaust pipe. It focuses and launches two opposing jets of plasma and radiation, punching their way out through the star's outer layers at velocities within a fraction of a percent of the speed of light. These are relativistic jets, and if one of them is fortuitously aimed at Earth, we witness the entire event as a long-duration gamma-ray burst. The initial flash is the jet breaking through the stellar surface, and the sustained emission is the continuous feeding of this cosmic engine as it consumes the remains of the star. The story for a short gamma-ray burst is different in its origin but shares the same terrifying finale, the sudden creation of a black hole. Here, the protagonists are two neutron stars, the ultra-dense, city-sized cores left over from previous supernova. Locked in a gravitational embrace, these stellar corpses orbit each other, slowly losing energy by radiating gravitational waves. Over hundreds of millions of years, their orbit shrinks until they finally collide in a spectacular and violent merger. When they touch, the result is not a gentle combining. It is a cataclysmic impact that releases a tremendous amount of energy and spews a cloud of neutron-rich material into space, material that rapidly forms heavy elements like gold and platinum. For a brief moment, the merged object might form a hypermassive neutron star, but it is almost always too heavy to be stable. It lasts for only a fraction of a second before its own gravity wins, and it too collapses directly into a black hole. Just as with the collapsing massive star, the leftover debris forms a hot, massive accretion disk around this brand new black hole. The same basic engine mechanism then kicks in, the conversion of gravitational energy into focused beams of radiation. The magnetic fields and neutrino interactions in the disk channel tremendous energy into two jets that blast outward. Because the neutron-star merger lacks the massive stellar envelope that a collapsing star possesses, there is no prolonged struggle to break free. The jets can exit almost immediately, resulting in the characteristically brief flash of a short gamma-ray burst. In both cases, long and short, the gamma-ray burst is the direct observational signature of a black hole being born, and almost instantly powering up to become one of the most efficient and powerful engines in the cosmos. This concentrated beaming of energy is the single most important factor that explains how these events can be so impossibly bright. Instead of the explosion's energy spreading out evenly in all directions like a sphere, it is focused into two narrow cones shooting out from the poles of the collapsing system. This is the difference between a standard light bulb and a laser pointer. Both might use the same amount of power, but the laser's light is concentrated into a tight beam, making it appear intensely bright to anyone standing directly in its path, while being completely invisible to anyone just a few degrees to the side. For a gamma-ray burst, this beaming effect is on a cosmic scale. The jets are astonishingly narrow, typically only a few degrees wide. To visualize that, hold your hand out at arm's length and make a peace sign. The space between your two fingers is roughly the width of a typical gamma-ray burst jet. Now imagine all the energy equivalent to a sun's entire lifetime output being forced through that tiny window. The material within these jets is not just moving fast, it is relativistic, meaning it is traveling at a significant fraction of the speed of light, often 99.99% or more. This has profound consequences. As matter is accelerated to these extreme velocities, it becomes focused and collimated, much like water forced through a nozzle. The physics within the jet are governed by some of the most intense magnetic fields and shock waves in the universe, which are responsible for generating the initial flash of gamma rays. Because the energy is not wasted by exploding in all directions, the brightness along the narrow axis of the jet is amplified to almost unimaginable levels. This is why a gamma-ray burst can momentarily outshine every star in its host galaxy combined. We are looking directly down the barrel of the universe's most powerful cannon. This geometry also presents a sobering statistical reality. For every brilliant gamma-ray burst we detect, there are hundreds, perhaps thousands, of similar events that occur but go completely unnoticed because their jets are pointed in other directions, away from our line of sight. We only see the ones where the deadly beam is aimed directly at us. This makes the study of these events a game of cosmic chance. Our satellites are blind to the vast majority of these explosions, meaning that the violent deaths of massive stars and the mergers of neutron stars are actually far more common throughout the universe than our detection rate would suggest. Every alert from Swift or Fermi represents a rare and fortunate alignment, a catastrophic event in a distant galaxy whose lethal beam just happens to be pointing our way, allowing us a brief but spectacular glimpse into the physics of the extreme. For astronomers, the Holy Grail wasn't just detecting a gamma-ray burst, it was to see what kind of stellar corpse it left behind. The theoretical link between long GRBs and the deaths of massive stars was strong, but science demands direct evidence. That proof arrived in a spectacular fashion in 1998, with an event that would forever bind these two cosmic phenomena together. On April 25th, the satellites picked up a strong burst, designated GRB 980425. What made this one different was its proximity for a GRB. It was practically in our backyard, at a redshift of just 0.0085. This closeness meant its afterglow would be bright, and any accompanying supernova would be visible. As the brilliant afterglow in visible light began to fade over the subsequent days and weeks, astronomers noticed something extraordinary. Instead of continuing to dim smoothly, the light curve developed a distinct bump. It began to brighten again, taking on a specific shape and color that seasoned supernova hunters recognized instantly. This was no mere echo of the burst, it was the unmistakable signature of a supernova rising from the ashes. Designated SN 1998 BW, this was the first supernova ever to be conclusively linked to a gamma-ray burst. The cataclysm wasn't just a theoretical model anymore, it was an observed fact. A massive star had died, and in its death throes, it had produced both a brilliant gamma-ray burst for those looking down the jet's axis and a spectacular supernova for observers watching from any other angle. But this was not just any supernova. Through detailed spectral analysis, it was identified as a very specific type, a broad-line type Ike supernova. This classification is packed with meaning. Type Ike tells us that the progenitor star had already lost its outer layers of hydrogen and helium before it exploded, likely stripped away by powerful stellar winds or interactions with a binary companion. This left behind a bare, massive core rich in heavier elements like oxygen and carbon. The broad-line descriptor is the real key. The spectral lines from the exploding material were incredibly wide and blurred, a telltale sign that the ejector was expanding at an enormous velocity, up to 30,000 kilometers per second, about 10% the speed of light. This extreme speed is the direct result of the extra kick provided by the GRB engine. A typical supernova can't achieve such velocities. It requires the immense energy injection from the relativistic jets punching their way out of the star to accelerate the debris to such fantastic speeds. This established a powerful cosmic connection. Long-duration gamma-ray bursts are the harbingers of broad-line type Ike supernova. They are two sides of the same catastrophic coin. The GRB is the narrowly beamed, ultra-relativistic jet we see only if we are perfectly aligned. The supernova is the more spherical, but still incredibly energetic, explosion of the star's outer layers that is visible from most viewing angles. One event, two spectacular displays. For more distant GRBs, spotting the supernova component becomes a monumental challenge. Its light is much fainter than the brilliant afterglow and is often lost in the glare. But by carefully monitoring the light curve for months, astronomers can subtract the fading afterglow and find the hidden supernova bump underneath, its characteristic rise and fall peeking through the data. Each successful detection, from nearby events to more distant ones, reinforces this fundamental link. proving that the collapse of a massive, stripped envelope star is the universal engine behind these long-duration cosmic fireworks. While these stellar explosions are dazzling cosmic spectacles when viewed from a safe distance, their unimaginable power forces us to confront a sobering question. What would happen if one of these events occurred not billions of light years away, but within our own cosmic neighborhood, and its deadly beam was aimed directly at us? The answer paints a scenario that, while statistically almost impossible, stands as one of the most potent existential threats in the universe's arsenal. A nearby gamma-ray burst, defined as one occurring within our own Milky Way galaxy and oriented with its jet pointed at Earth, would be an event of unparalleled catastrophe, not with fiery explosions or incoming debris, but through a silent, invisible attack on the very shield that protects all life on our planet. The immediate effects would be deceptively spectacular. The initial gamma-ray flash, traveling at the speed of light, would offer no warning. One moment the night sky would be normal, the next a second sun would appear, blazing with the light of 1,000 full moons, but shining in gamma rays and X-rays invisible to our eyes. Specialized satellites would scream in alarm as their detectors were overwhelmed, but for most people on the planet, the first sign would be a brilliant, silent flash in the sky that would last for tens of seconds. This would not be a heat ray that sets cities ablaze. The energy would be too diffuse by the time it crossed interstellar space. Instead, the real danger would begin in the upper atmosphere, where this wave of high-energy radiation would trigger a chain of chemical reactions with devastating consequences. The primary and most lethal impact would be on Earth's ozone layer. This thin, fragile blanket of ozone gas high in the stratosphere is our planet's primary defense against the sun's harmful ultraviolet radiation. The incoming gamma rays would rip apart molecules of nitrogen and oxygen, creating vast quantities of nitrogen oxides. These compounds are voracious ozone destroyers, acting as a catalyst to break ozone, or O3, back down into ordinary oxygen, or O2. Computer models of such an event suggest that a gamma-ray burst occurring within 6,000 light-years of Earth could deplete the ozone layer by 30 to 50% globally, with the hemisphere facing the burst experiencing losses of up to 90%. This would not be a temporary hole like the one over Antarctica. It would be a catastrophic, planet-wide thinning of our UV shield that could take a decade or more to recover. With our protective layer stripped away, the surface of the Earth would be bathed in intense, mutagenic ultraviolet radiation from our own sun. The effects on the biosphere would be apocalyptic. Phytoplankton, the microscopic plants that form the base of the entire marine food web, are highly susceptible to UV damage. A massive die-off would trigger a collapse of ocean ecosystems. On land, plants would suffer from severe radiation damage, stunting growth and crippling agriculture. Animals, including humans, would suffer from horrific sunburns within minutes, along with drastically increased rates of skin cancer and cataracts. The DNA of countless organisms would be damaged, leading to widespread mutations and population crashes. The fossil record suggests this may not be pure speculation. Some scientists have proposed that a gamma-ray burst could have been responsible for the Ordovician mass extinction 450 million years ago, which wiped out nearly 85% of marine species and coincided with a period of intense glaciation that could also be explained by the atmospheric effects of a burst. Beyond the UV onslaught, the event could trigger other secondary climatic horrors. The same chemical reactions that destroy ozone also produce nitrogen dioxide, a brownish gas that would scatter sunlight and paint the skies with a hazy, dirty glow. This smog could potentially block a significant amount of sunlight from reaching the surface, plunging the planet into a sudden, cosmic winter that could last for years, devastating global agriculture and collapsing food chains that rely on photosynthesis. Furthermore, the gamma rays would likely create a thick layer of nitrogen dioxide gas in the upper atmosphere that would be highly effective at absorbing outgoing thermal radiation from the Earth's surface, potentially causing a sharp and sudden spike in global temperatures. A bizarre scenario where the planet could experience a bitter winter at the surface while the upper atmosphere bakes. This combination of ozone destruction, altered climate, and increased radiation would create a perfect storm of extinction pressures, unlike any other natural disaster in Earth's history. And it's this very understanding of how they die that allows these events to become something even more profound, tools for measuring the cosmos itself. For over a century, astronomers have relied on what they call standard candles objects with a known intrinsic brightness. By comparing how bright an object appears to us with how bright we know it actually is, we can calculate its distance. It's like knowing the exact wattage of a light bulb. The fainter it appears, the farther away it must be. The most famous of these cosmic yardsticks are Type Ia supernova, which have a very predictable peak brightness. Their discovery in the late 1990s led to the shocking revelation that the expansion of the universe is not slowing down, as everyone had assumed, but is actually accelerating, driven by a mysterious force we now call dark energy. But supernova, for all their utility, have their limits. We can only see them out to a certain distance. To truly test our models of the universe's expansion and the nature of dark energy, we need to push our measurements deeper into the cosmos, to times when the influence of dark energy was just beginning to be felt. This is where gamma-ray bursts enter the picture as the next generation of cosmic yardsticks. Their incredible luminosity means they can be seen clear across the observable universe, far beyond the reach of even the most powerful supernova surveys. The challenge, of course, is that unlike Type Ia supernova, GRBs are not identical. Their energies vary wildly. A burst from a collapsing star in a nearby galaxy can appear similar to one from the edge of time, making it impossible to use them as simple standard candles. However, astronomers are a clever bunch. Instead of giving up, they went looking for a way to standardize them. They realized that while the total energy of a burst might be all over the map, certain relationships between its different observable properties might hold true across all events, a kind of universal signature. After years of painstaking analysis on hundreds of bursts, they began to find these correlations. One of the most promising is known as the Amati relation, named after the Italian astrophysicist who discovered it. It describes a tight connection between the intrinsic peak energy of the gamma-ray emission and the total energy released in the burst. In simpler terms, the brighter the burst is at its highest energies, the more total energy it likely released. Another key correlation is between the luminosity of the afterglow and the time it takes for that afterglow to fade by a certain amount. Think of it like this. If you see two different car headlights from a distance, one might be from a small car and one from a large truck. They aren't standard candles. But if you could measure how quickly their brightness changes as the cars turn a corner, you might find a relationship that lets you calculate the true power of the headlight based on its fading pattern. That's what astronomers do with GRBs. By carefully measuring these properties, the peak energy, the fading timescale of the afterglow, they can essentially calibrate each individual burst. They can use these correlations to estimate its true, intrinsic luminosity. Once they know that, they can then calculate its distance, just like with a standard candle. This turns each distant gamma-ray burst into a lone beacon in the darkness, a signpost whose distance we can estimate independently of other methods. By building a large sample of these standardized GRBs, stretching from the nearby universe all the way back to the cosmic dawn, cosmologists can trace the history of the universe's expansion over an enormous stretch of time. They can see if the rate of acceleration has changed and put our models of dark energy to the ultimate test. While the uncertainties are still larger than those from supernova, the sheer distance GRBs can probe makes them an invaluable independent check. They provide a crucial cross-verification for the results we get from other techniques, helping to ensure that our understanding of the universe's fate isn't built on a single, potentially flawed measurement. They are the long-range scouts in our quest to map the geometry and expansion history of the entire cosmos. Just when astronomers thought they had gamma-ray bursts neatly sorted into the short and long categories, the universe presented a new enigma, a class of events so bizarre they defy the established rules. We call them ultra-long gamma-ray bursts, and they are the true marathon runners of the cosmic explosion world. While a typical long GRB is impressive for its few minutes of fury, an ultra-long event can persist for hours, sometimes even tens of thousands of seconds. That's not a flash, that's a sustained, high-energy siege that can last throughout an entire night of observations, completely upending our models of how these cosmic engines operate. The existence of these ultra-long bursts immediately pointed toward a different kind of powerhouse, the classic collapsar model, where a massive star collapses into a black hole and powers a jet for a minute or two, simply can't explain an event that lasts for several hours. The fuel reservoir provided by a single star's outer layers would be consumed far too quickly. This forced scientists to consider an even more monstrous and dramatic scenario, the tidal disruption of a star by a supermassive black hole. Imagine a star like our Sun wandering too close to the gravitational grip of a black hole weighing millions of solar masses. The immense tidal forces would literally stretch and pull the star apart into a long, thin stream of gas in a process picturesquely known as spaghettification. This stream of stellar debris then swirls around the black hole, forming a vast, chaotic accretion disk that feeds material into the black hole over a much longer timescale. This prolonged feeding could, in theory, power relativistic jets for hours or even days, creating the signature ultra-long gamma-ray burst. It's a stellar death by prolonged consumption rather than a sudden core collapse. But the plot thickens when we consider their presence in the early universe. Detecting an ultra-long burst at a high redshift would be a monumental discovery, as it would suggest that the supermassive black holes necessary to cause such a disruption were already in place and active when the cosmos was very young. This presents a fascinating puzzle for cosmologists. How did black holes grow to such immense sizes so quickly after the Big Bang? An ultra-long GRB at a redshift of 6 or 7 would act as a direct beacon, signaling the existence of a fully formed supermassive black hole in the cosmic dawn, forcing us to rethink our models of how these gravitational giants form and evolve. Each one of these rare, drawn-out events is a potential key to understanding the rapid assembly of the first galaxies and the monstrous black holes at their hearts, making them not just a curiosity, but a crucial piece of the puzzle of cosmic structure. While we've explored the depths of massive stars that form black holes, there exists an even more extreme and hypothetical fate for the true titans of the cosmos, a scenario so violent it would make a typical gamma-ray burst seem tame. This brings us to the elusive and theoretical pair instability supernova, an explosion of such staggering scale that the star doesn't just collapse, it completely annihilates itself in a blast that tears it apart from the inside out, leaving nothing behind, not even a black hole. The hunt for a gamma-ray burst linked to one of these events is one of the most intense pursuits in modern astrophysics, a quest to find evidence for a star so massive it fundamentally challenges our understanding of stellar limits. To understand what makes this explosion so unique, we need to venture into the core of a true stellar behemoth, a star with a mass between 150 and 300 times that of our Sun. Within the furnace of its core, temperatures and pressures reach such insane levels that the photons of light themselves, which normally provide the radiation pressure holding the star up, begin to behave differently. At these extreme energies, a photon can spontaneously create a pair of particles, an electron and its antimatter counterpart, a positron. This process, known as pair production, is a theft of energy from the star's very heart. The radiation pressure that was fighting against gravity suddenly drops as the energy that was creating it is now being converted into matter. This loss of pressure is catastrophic. The core, no longer supported from within, begins to contract under its own immense weight. This contraction isn't a gentle sag, it's a runaway collapse that raises the temperature even further, like pumping the bellows on a forge. But here's where the story diverges from a typical supernova. In this supermassive star, the rising temperature triggers the runaway fusion of oxygen in the core. This isn't a controlled burn, it's a thermonuclear bomb of unimaginable proportions. The energy release from this explosive oxygen fusion is so instantaneous and so powerful that it doesn't just halt the collapse, it reverses it completely. The entire star, from its core to its outer layers, is blown to smithereens in a titanic explosion that can briefly outshine an entire galaxy. Every last bit of the star is vaporized and scattered into space, leaving no remnant behind. There is no neutron star and no black hole. The stellar corpse is entirely erased from existence. So where does the gamma-ray burst come in? The prevailing theory suggests that even in this total self-destruction, the physics could still conspire to create a narrowly focused jet. The explosion itself would be overwhelmingly spherical, but the rapid rotation of such a massive star or the presence of a strong magnetic field might be able to channel a fraction of the energy into bipolar outflows. If one of these relativistic jets were pointed at us, we might see it as an incredibly luminous, long-duration gamma-ray burst. However, its light curve and spectral signature would be completely unique, bearing the unmistakable hallmarks of this specific ultra-energetic detonation. The search for this signature is what drives astronomers to sift through the data of every long GRB with extra care. They are looking for telltale clues in the aftermath. The spectroscopic fingerprint of the supernova accompanying the burst would be utterly distinct. A pair instability supernova would synthesize and eject a colossal amount of radioactive nickel, dozens of solar masses worth. The decay of this nickel would power a supernova light curve that would be anomalously bright and persist for much longer than a typical broad-line type Ike event. The chemical composition of the ejected material would also be a dead giveaway, expected to be rich in specific elements and devoid of others. Finding a GRB whose afterglow fades to reveal this kind of hyper-energetic, nickel-powered supernova rising in its place would be the smoking gun, the definitive proof that we have witnessed the ultimate stellar death. These cosmic leviathans are thought to have existed primarily in the early metal-poor universe, making the most distant gamma-ray bursts the prime hunting ground for these elusive events. Every time a high redshift burst is detected, there is a surge of excitement and a frantic effort to secure time on the world's most powerful telescopes, like the James Webb Space Telescope, to look for these specific signatures in the fading afterglow. While the prize has not yet been claimed, the very search pushes our observational capabilities to their limits and refines our models of stellar physics under the most extreme conditions imaginable. The discovery of a pair instability supernova GRB would do more than just add a new class of explosion to the catalogue. It would confirm the existence of a population of stars whose size and power we can barely comprehend, proving that the early universe was a place where the rules of physics were tested to their absolute breaking point. The sheer violence of a gamma-ray burst is difficult to overstate, but its true cosmic significance might not be in the destruction it causes, but in the possibilities it prevents. To understand this, we need to shift our perspective from the grand scale of galaxies to the delicate, nascent environments where planets, and perhaps life itself first begin to coalesce. In the early universe, during that turbulent era when the first stars were exploding as GRBs, every corner of a young galaxy was a potential construction site for new solar systems. Protoplanetary disks, those swirling clouds of gas and dust around infant stars, are the cradles of planets. Within them, dust grains gently collide and stick together, slowly building the rocky cores of future worlds in a process that requires millions of years of relative calm. Now inject a gamma-ray burst into this scene, A nearby event, perhaps within a few thousand light-years, would unleash a torrent of high-energy radiation that would not merely interrupt this process, it would fundamentally scorch the building site. The initial flash of gamma rays and X-rays would blast through a protoplanetary disk like a cosmic hurricane. For the dusty grains that are the building blocks of terrestrial planets, the impact would be catastrophic. The intense radiation would heat these tiny particles to incredible temperatures, potentially vaporizing them entirely or charging them electrostatically to the point where they repel each other instead of sticking together. This could effectively halt the critical first steps of planet formation, shattering the delicate accretion process and sterilizing the disk of the material needed to form Earth-like worlds. But the damage would extend far beyond simply melting dust. The same chemical reactions that would later threaten Earth's ozone layer in a doomsday scenario would also play out on a local scale within the planet-forming disk itself. The radiation would shatter complex molecules, the precursors to water and organic compounds, that might have been slowly accumulating on the surfaces of dust grains or within the icy mantles of cometesimals. In an instant, these probiotic building blocks, which could have eventually been delivered to new planets to seed them with the ingredients for life, would be broken down into their constituent atoms. The disk, once a reservoir of potential, would be left a chemical wasteland, its complex molecular inventory reset to zero. This leads to a profound and sobering implication for the story of life in the universe. The era of the first stars was also the era of the most frequent gamma-ray bursts. Galaxies in the early universe were smaller, denser, and more actively forming stars, creating the perfect conditions for these catastrophic explosions to occur with relative frequency. This means that for billions of years, the universe may have been a profoundly hostile place for the emergence of life. Entire galaxies, or large regions within them, could have been repeatedly scrubbed clean by successive GRBs, their planetary systems sterilized or aborted before they could even properly form. Life, as we understand it, may have had to wait for the cosmic violence to settle down, for the rate of GRBs to decline as the universe aged and galaxies evolved, before it could finally gain a foothold in pockets of calm. This concept introduces a potential new filter in the Fermi paradox, the question of why we haven't seen evidence of other intelligent life. It suggests that the window for life's emergence might not just be about a planet being in the right place, but about it forming at the right time. A planetary system that forms too early, in a galaxy still rife with massive stars and frequent GRBs, might have its chances at developing a complex biosphere permanently erased. We on Earth may be the beneficiaries of cosmic timing, having formed some 9 billion years after the Big Bang, long after the peak of gamma-ray burst activity had passed. Our solar system arose in a relatively quiet suburban neighborhood of a mature galaxy, granting it the billions of years of stable peace required for life to evolve from single cells to a civilization that can look back and ponder the very explosions that might have made our existence possible. The most distant GRBs, therefore, are not just historical relics. They are markers of a violent past that may have dictated the very schedule for when and where life could finally flicker into existence in the cosmos. This preference for a more pristine environment isn't a minor detail. It's a fundamental clue about the very nature of the stars that can produce these cosmic explosions. To understand why, we need to look at the life cycle of a massive star. A star's metallicity profoundly influences its behavior from birth to death. Stars forming from gas that is rich in heavier elements, like the stuff our sun is made from, behave differently than those born from the pure hydrogen and helium that filled the early cosmos. These heavier elements make the gas cloud more opaque and efficient at cooling itself, allowing it to fragment into many smaller stars. This is why in metal-rich galaxies like our own Milky Way, we see plenty of stars, but most are of low to intermediate mass. But in a low metallicity environment, the game changes entirely. Without those heavier elements to aid cooling, gas clouds can't fragment as easily. This leads to the formation of far fewer but much more massive stars. The universe essentially builds colossal stellar titans, the perfect progenitors for long gamma-ray bursts. Furthermore, metals play a crucial role in stellar winds. In a high metallicity star, the presence of heavy atoms allows the intense radiation pouring out from the core to push significant mass away from the star's surface over its lifetime. Think of it like a constant, powerful solar wind on a colossal scale. This mass loss has two critical consequences. First, it steadily reduces the star's mass, potentially making it too small to form a black hole by the time its core collapses. Second, and perhaps more importantly, this shedding of mass acts as a brake, slowing down the star's rotation as angular momentum is carried away with the ejected material. A fast spinning core is non-negotiable for generating a gamma-ray burst. It's the star's rotation that helps form the accretion disk around the newborn black hole and powers the intense magnetic fields that collimate the jets. A slow spinning core might just fizzle into an ordinary supernova. A low metallicity star, however, has a huge advantage. With few heavy elements in its outer layers, its stellar winds are much weaker. It holds onto its mass tenaciously, remaining massive enough for a dramatic collapse, and crucially, it retains its rapid spin right up to the very end of its life. This preserves the essential ingredient needed to transform a mere stellar collapse into a universe-spanning gamma-ray beam. This elegant explanation perfectly aligns with the observed abundance of distant bursts. The early universe was a place of incredibly low metallicity. The first few generations of stars had yet to seed their galaxies with the heavy elements forged in their cores and scattered by their supernova. This meant the conditions were ideal for the formation of these massive, fast-spinning stars that die as GRBs. As the universe aged, succeeding generations of stars polluted the interstellar medium with metals. While this enrichment was essential for forming rocky planets and ultimately life, it also made galaxies increasingly hostile to the formation of gamma-ray burst progenitors. The rate of long GRBs in the local, metal-rich universe is consequently much lower. We are, in a sense, living in a cosmic epoch where the most spectacular fireworks show is winding down, its prime time having passed billions of years ago. The distant bursts we detect are therefore more than just ancient explosions. They are fossils of a bygone era, a time when the universe was younger, simpler in its composition, and far more violent in its stellar deaths. Yet for all their mind-bending power, gamma-ray bursts are typically fleeting ghosts in the machine, their brilliance captured only by sensitive satellite detectors. But on one extraordinary occasion, the universe provided a demonstration of their raw energy so spectacular that it briefly stepped out of the realm of astrophysical data and became a direct, visceral human experience. This was GRB 080319b, an event that earned the nickname the Clark event, and for a breathtaking half-minute, became visible to the naked eye from Earth despite having begun its journey to us when our planet was less than half its current age. The story begins on the morning of March 19, 2008. The Swift satellite was dutifully monitoring the sky when its burst alert telescope was triggered by a colossal surge of gamma rays. This was no ordinary burst. The intensity was so overwhelming that it temporarily saturated Swift's detectors, a clear sign that something exceptionally powerful was happening. Within moments, Swift autonomously slewed to bring its X-ray and optical telescopes to bear on the location. At virtually the same time across the globe, an orbiting telescope named CONUS Wind and the European Space Agency's Integral Observatory also registered the event, their instruments screaming under the deluge of high-energy photons. The initial data was so intense that astronomers initially thought the burst must be incredibly close, perhaps within our own galactic neighborhood. The reality was almost incomprehensibly more impressive. What made this burst truly historic was what happened next on Earth. In countries with dark skies, particularly across Europe and Asia where it was nighttime, something remarkable occurred. For approximately 30 seconds, a point of light flared into existence in the constellation Boötes. It wasn't a faint glimmer requiring averted vision. It shone at a peak magnitude of 5.3. This means that for anyone looking at the right patch of sky away from city lights, this cataclysm 7.5 billion light-years away was briefly as visible as the faintest stars in the Little Dipper. A human being, using nothing but their own eyes, could witness the death scream of a star in a galaxy so distant that its light had been traveling for over half the age of the universe. The physics behind this unprecedented visibility is a testament to almost unimaginable energy. The redshift of the burst was measured at 0.937, placing its source a staggering 7.5 billion light-years from Earth. For its light to reach us with such apparent brightness across that gulf of expanding space, the intrinsic luminosity of the explosion had to be beyond calculation. Astronomers estimate that in those first few seconds, the burst was releasing energy at a rate of 2.5 times 10 to the 54th power ergs per second. To put that number in perspective, that is equivalent to the Sun's entire energy output over 10 billion years being emitted every single minute. And all of that power was focused into two narrow jets, one of which was pointed with near-perfect precision directly at our solar system. We weren't just watching this event, we were looking directly down the barrel of the most powerful cannon ever observed in the universe. The afterglow of GRB 080319b provided the final, crucial pieces of the puzzle. Observations from dozens of telescopes revealed an exceptionally clear and simple light curve, one that aligned beautifully with the standard fireball model of gamma-ray burst. There was no evidence of dense material surrounding the progenitor star, suggesting it had effectively shed its outer hydrogen envelope, leaving a bare, massive Wolf-Rayet-type core primed for collapse. The lack of obstructions allowed the relativistic jet to escape cleanly and efficiently, channeling virtually all of that catastrophic energy into a clean, brilliant beam of light. Its remarkable visibility wasn't a fluke of different physics. It was the perfect alignment of a massive, stripped progenitor star, a fast-rotating core, and a flawless aim directly at Earth. It was a cosmic bullseye of historic proportions, a reminder that for all our advanced technology, the universe can still offer a show that requires no equipment at all to appreciate, if only for a fleeting, glorious moment. And while missions like SWIFT and Fermi have revolutionized our ability to catch these fleeting events, the next great leap in our understanding of the most distant gamma-ray bursts will come from an observatory with a completely different purpose, one designed to stare down the universe not in gamma rays but in visible light. The Vera C. Rubin Observatory, currently nearing completion atop a mountain in Chile, represents a fundamental shift in how we observe the cosmos. Its mission isn't to rapidly respond to alerts from other telescopes, but to conduct an unprecedented, decade-long movie of the entire southern sky. This monumental project, known as the Legacy Survey of Space and Time, or LSST, will use its massive 8.4-meter mirror and a gargantuan 3.2 gigapixel camera to scan the entire available sky every few nights, detecting changes and transient events on a scale we can barely imagine. This relentless, all-seeing eye will transform the hunt for gamma-ray burst afterglows from a targeted pursuit into a wholesale harvest. Instead of waiting for a satellite to provide coordinates that we then rush to observe, the LSST will simply see them appear. Night after night, as it compares new images to its deep reference maps of the sky, it will automatically flag new points of light that weren't there before. Among the millions of transient events it will catalog, from nearby supernova to flaring stars and moving asteroids, will be the brilliant, fading afterglows of gamma-ray bursts. Current estimates suggest the LSST could detect the optical afterglows of up to several thousand GRBs over its 10-year survey, a number that dwarfs the entire catalog we've painstakingly assembled over the past 3 decades. It will find them indiscriminately, including those that were missed by gamma-ray satellites because their jets were slightly off-axis or whose initial flash was too faint to trigger an alert. The true power of this approach lies in its statistical might and its incredible depth. By finding so many afterglows, the LSST will build a vast, unbiased sample of GRBs that will allow us to finally understand the full population. We will see the full range of their brightness, duration, and host environments. But more importantly for our journey to the edge of time, the LSST's enormous light-gathering power means it will see fainter objects than any similar survey before it. This is the key to probing the high redshift universe. The afterglow of a gamma-ray burst at a redshift of 8 or 9 is incredibly faint, often requiring long exposures on the world's largest telescopes just to get a single detection. The LSST, with its vast mirror and sensitive camera, will be able to detect these faint, high redshift embers directly in its wide-field images. It won't just find a handful of these extreme events. It could discover dozens, perhaps even over 100 GRBs from the first billion years of the universe. Each one of these high redshift discoveries will be a precious gift for follow-up. The moment the LSST automated pipeline identifies a new, fading point of light as a potential GRB afterglow, it will instantly broadcast its coordinates to the world. This will trigger a global armada of telescopes, from the James Webb Space Telescope in orbit to every major ground-based observatory, to swing into action. With the LSST providing a precise location and a detailed measurement of the afterglow's brightness and fading rate from its very first moments, these follow-up observations will be far more efficient and insightful. Astronomers will know exactly which targets are the most promising for spending precious time on spectroscopic observations to measure redshift. The LSST effectively acts as the ultimate spotter, guiding our most powerful instruments to the most valuable targets in the sky night after night. This flood of new data will do more than just add numbers to a catalog. It will allow us to map the history of stellar death and metal enrichment across cosmic time. By tracing the rate of gamma-ray bursts from the local universe all the way back to the cosmic dawn, we can track the formation rate of massive stars throughout history. Since GRBs are linked to the deaths of these specific stars, their frequency acts as a direct tracer of star formation in the early universe, potentially providing a more accurate measure than other methods. Furthermore, by studying the properties of the host galaxies of these distant bursts galaxies that would be far too faint to find on their own, we can understand the conditions that bred these stellar titans. The Vera Rubin Observatory's legacy survey of space and time won't just find more gamma-ray bursts. It will open a new window into the most violent and formative chapters of our cosmic history, painting a dynamic picture of how the universe built itself up from the first stars to the galaxies we see today. This brings us to a tool that was practically built for this specific task, the James Webb Space Telescope. While missions like SWIFT are the rapid responders that first alert us to these events, Webb is the deep space forensic analyst that steps in to conduct the detailed investigation. Its entire design is optimized for one primary goal: to see the first stars and galaxies that ignited after the Big Bang. And since the most distant gamma-ray bursts are the death cries of those very first stars, Webb is the perfect instrument to hunt them down and decipher their secrets. The key to its success lies in its incredible infrared vision. As we've discussed, the light from an object at the edge of the observable universe is stretched so dramatically by the expansion of space that it is shifted entirely out of the visible spectrum and into the infrared. This is a fundamental problem for ground-based telescopes and even for Hubble, which sees primarily invisible and ultraviolet light. The Earth's atmosphere itself glows brightly in the infrared and blocks most of these signals, making high redshift afterglows nearly impossible to detect from the ground. Webb, positioned at the stable Lagrange point 2, far beyond the interference of our atmosphere, and with its instruments permanently cooled to within a few tens of degrees of absolute zero, is uniquely positioned to see this cold, faint, ancient light with a clarity never before possible. When a satellite like Swift or Fermi identifies a candidate for a high redshift burst, the astronomical community kicks into a highly coordinated dance. Teams rapidly submit target of opportunity proposals to interrupt Webb's meticulously planned observing schedule. If approved, the massive golden mirror swiftly turns toward the coordinates, its instruments poised to capture the fading ember. Webb doesn't just take a simple picture, it uses its near-infrared spectrograph NIRSpec to dissect the afterglow's light into a detailed spectrum. This is where the real magic happens. That spectrum contains the faint fingerprints of elements in the gas around the burst and along its line of sight, but most importantly, it reveals the unmistakable signature of the Lyman alpha break, the definitive proof of an extreme redshift. Webb's sensitivity allows it to obtain this critical data from afterglows that would be completely invisible to any other telescope, turning a candidate into a confirmed record breaker from the cosmic dawn. But Webb's role extends far beyond just measuring distance. Its powerful instruments can analyze the chemical composition of the burst's environment and its host galaxy. By studying the specific absorption lines in the spectrum, astronomers can determine the metallicity, the abundance of elements heavier than hydrogen and helium in the gas surrounding the progenitor star. This tells us about the generation of stars that came before it. A very low metallicity would be a strong indicator that we are indeed looking at the death of one of the universe's first stellar generations, a population Roman III star. Furthermore, Webb can directly image the host galaxy long after the afterglow has faded away. These nascent galaxies are typically far too faint and small to be found on their own, but the GRB acts as a brilliant pin on a cosmic map guiding Webb right to it. We can then study the structure, size, and star-forming activity of this incredibly distant galaxy, learning about the conditions that bred such a monstrous star. In this way, a single distant gamma-ray burst observed by Webb becomes a multi-purpose cosmic observatory. It's not just a flash in the dark, it's a backlight illuminating the early universe, a time capsule from the era of reionization, and a signpost to the earliest building blocks of galaxies. With each one it observes, Webb helps us piece together the story of how the first stars lived, died, and through their cataclysmic deaths, seeded the cosmos with the heavy elements that would eventually form planets and life. It is using the most violent explosions in the universe as tools to gently uncover the deepest secrets of our cosmic origins. And yet, even with this incredible focus, the true power of a gamma-ray burst isn't just in the light it emits, but in the ripples it can send through the very fabric of spacetime itself. For decades, the study of these cosmic explosions was confined to the electromagnetic spectrum, the domain of light, from gamma rays to radio waves. But a monumental discovery in 2017 shattered that limitation forever, weaving GRBs into a far richer cosmic tapestry and opening a whole new sense with which to perceive the universe. This was the event known as GW170817, a detection that didn't just link two phenomena, it fused them into a single multi-messenger story, confirming a long-held theory about the origin of short gamma-ray bursts in the most dramatic way possible. On August 17, 2017, at precisely 12:41 Universal Time, the twin detectors of the Laser Interferometer Gravitational Wave Observatory, or LIGO, in the United States, along with the Virgo detector in Italy, registered a signal unlike any they had seen before. It wasn't the signature chirp of two black holes merging which had been detected before. This was a longer, richer signal lasting approximately 100 seconds. The data told a clear story. Two neutron stars, each about 1.4 times the mass of our Sun, had been locked in a final, fatal spiral for over 100 million years. In their last moments, they circled each other thousands of times per second, radiating an immense amount of energy as gravitational waves ripples in space-time predicted by Einstein a century earlier. These ripples traveled across 130 million light-years of space before finally stretching and squeezing the arms of the LIGO and Virgo detectors by a distance 10,000 times smaller than a proton. Just 1.7 seconds after the gravitational wave signal ended, the Fermi Gamma-Ray Space Telescope and independently the Integral Satellite detected a short, weak gamma-ray burst, designated GRB 170817A. The chance of this being a coincidence was astronomically small. The timing and the sky location, which was rapidly triangulated using the combined data from the 3 gravitational wave observatories, left no doubt. For the first time in history, humanity had both heard the space-time ripples and seen the light from the same cosmic cataclysm, the merger of 2 neutron stars. The gravitational waves carried the detailed story of the inspiral and merger itself, while the gamma-ray burst was the brilliant flash of the relativistic jet launched in the aftermath. This single event transformed astrophysics, moving the study of GRBs from a one-dimensional observation into a multi-dimensional experience. The aftermath of this event was a global scientific frenzy unlike any other. The gravitational wave data provided a treasure map, narrowing down the location of the source to a region of the sky containing about 36 galaxies. Astronomers around the world pointed every available telescope at that patch of sky, and within hours, a team using the SWOPE telescope in Chile found it, a new point of light in the galaxy NGC 4993. This was the kilonova, the radioactive glow of the material ejected during the neutron-star merger. Over the following days and weeks, observatories across the electromagnetic spectrum tracked its evolution. They witnessed the creation of staggering amounts of heavy elements like gold, platinum, and uranium, proving definitively that these cosmic collisions are the universe's primary forges for the heaviest elements in the periodic table. The neutron-star merger wasn't just making a black hole and a gamma-ray burst. It was literally seeding the galaxy with the building blocks for future planets and potentially life. This multi-messenger breakthrough cemented the origin story for short gamma-ray bursts. The brief, sub-2-second duration of the flash perfectly matched the theoretical models for a merger event. Unlike the collapse of a massive star, which takes time to unfold, a neutron-star merger is an incredibly violent and rapid collision, explaining the short, sharp nature of the gamma-ray signal. The event also solved another puzzle: why some short GRBs are faint. In the case of JWST, the gamma-ray burst was relatively weak. Data suggests this is because we were not looking directly down the barrel of the jet. We were seeing it from a slightly off-axis angle. This provided crucial insight into the geometry of these events and helped explain the diversity in brightness observed in other short bursts. The potential of this multi-messenger approach now stretches all the way back to the cosmic dawn. While current gravitational wave detectors like LIGO and Virgo are not sensitive enough to detect neutron-star mergers from the very early universe, next-generation observatories planned for space, like the Laser Interferometer Space Antenna, or LISA, will be. LISA will be able to detect the gravitational waves from neutron-star binaries as they slowly spiral together over millions of years, potentially predicting their mergers long before they happen. Imagine a future where we receive a gravitational wave alert from a binary system at a redshift of 8, telling us that a merger is imminent in 1,000 years. We could then point the most powerful telescopes of that era to that exact spot and wait, ready to capture the simultaneous gravitational wave and gamma-ray burst signal from the edge of time itself. This would allow us to study the properties of neutron stars and the equation of state of nuclear matter under conditions that existed in the universe's infancy, using these colossal events as natural laboratories for physics we could never recreate on Earth. The link between gravitational waves and gamma-ray bursts has opened a new chapter in astronomy, one where we don't just see the universe, but we can finally hear its deepest, most violent rhythms. But for all their brilliant afterglows that guide our telescopes, there exists a mysterious and frustrating class of these explosions that seem to break the rules, events that leave astronomers searching in the dark. These are the so-called dark gamma-ray bursts. The sequence is familiar. A satellite detects a brilliant flash of gamma rays. It swiftly relays the coordinates to observatories around the world, and within minutes, large optical telescopes swing into action, expecting to find a new pinprick of light fading in the void. Yet, for a significant fraction of these events, perhaps as many as half, they find nothing. The spot on the sky remains stubbornly, inexplicably black. The X-ray afterglow might be there, clearly visible to space-based telescopes, and a radio afterglow might even emerge days later, but the crucial visible light component is completely absent. It's as if the universe decided to stage the most spectacular fireworks show and then immediately threw a thick blanket over it. For years, this was a perplexing puzzle. The leading theory was that these bursts were just extremely distant. Their visible light redshifted so far into the infrared that optical telescopes simply couldn't see it. While this is true for some, it didn't explain all dark GRBs. The breakthrough in understanding came when astronomers, using the infrared vision of telescopes like Spitzer and later the James Webb Space Telescope, finally managed to track down the faint, heat-glowing embers of these events. They discovered that the visible light wasn't missing because it was redshifted, it was being stolen. The culprit, immense, dense clouds of cosmic dust within the burst's own host galaxy. Imagine the scene. A massive star lives its short, violent life surrounded by the very material from which it was born, a thick, swirling cocoon of gas and dust. When it finally explodes as a gamma-ray burst, the brilliant flash of optical and ultraviolet light from the afterglow doesn't get a clean getaway. It immediately slams into this surrounding shroud of microscopic dust grains. These grains, made mostly of carbon and silicate, are incredibly effective at absorbing visible light. They act like trillions of tiny black sponges, soaking up the photons and converting their energy into heat, which causes the dust to glow faintly in the infrared. To an optical telescope, the burst appears completely dark, while an infrared telescope sees a bright, warm glow. The afterglow is there, we just need the right kind of eyes to see it. This phenomenon is far more than a simple observational inconvenience. It's a vital clue about the environment in which these massive stars are born and die. A galaxy that is rich in dust is also a galaxy that is actively forming stars, as dust is a key ingredient in the process of stellar birth. Therefore, a dark gamma-ray burst is likely a signpost pointing to a particularly fertile stellar nursery, a region of its host galaxy that is still choked with the raw materials of creation. This makes perfect sense for the progenitors of long GRBs. They are massive stars that live fast and die young, exploding before they have time to travel far from their dusty birthplace. When we extend this logic to the early universe, the implications are profound. The first galaxies were not the elegant spirals we see today. They were likely smaller, denser, and far dustier than many models predicted. Intense bursts of star formation would have filled them with massive stars and the surrounding debris from their formation. A gamma-ray burst occurring in such an environment would almost certainly be a dark burst. Its brilliant optical afterglow would be immediately swallowed by the thick cosmic dust, leaving only the higher energy X-rays and the heat signature in the infrared to escape. This means our current census of the most distant GRBs, based largely on optical follow-up, is probably heavily biased. We are only seeing the ones that had a clear path for their light to escape, the exceptions rather than the rule. The early universe might have been teeming with these dark explosions, their stories hidden behind veils of dust, waiting for the infrared eyes of the James Webb Space Telescope to finally reveal them and show us the true, dusty nature of the cosmos in its infancy. Yet for all their power to pierce the veil of time, even gamma-ray bursts cannot shine from the absolute beginning. There exists a fundamental boundary, a cosmic horizon beyond which we cannot see, not because our telescopes are too weak, but because the universe itself was fundamentally different. This ultimate limit is defined by a redshift of around z equals 20, a frontier that represents a transition not just in distance but in the very nature of reality. To understand this barrier, we must journey back to a time before the first stars, before the first galaxies, even before the cosmic dark ages, to an era known as the photon decoupling epoch. Picture the universe at this time, a mere 380,000 years after the Big Bang. It is not a vast, empty expanse dotted with galaxies, but an incredibly dense, scorching hot fog, a near-perfect plasma of protons, electrons, and photons all constantly interacting. Light in this primordial soup is not free to travel. A photon couldn't journey more than a tiny fraction of an inch before being immediately scattered or absorbed by a free-flying electron. The entire cosmos is opaque, glowing with a uniform, blinding light, but utterly impenetrable to vision. This is the epoch of the cosmic microwave background radiation, the moment when the expanding universe finally cooled enough for electrons to combine with protons to form the first neutral hydrogen atoms. This event, known as recombination, was the universe's great clearing. With electrons now bound into atoms, the photons that had been constantly bouncing off them were suddenly set free. For the first time, light could travel across vast distances without being impeded. This is the source of the cosmic microwave background we detect today. It is the ancient flash of that first light finally breaking free, now cooled and stretched by 14 billion years of expansion into the microwave part of the spectrum. But this moment also creates our ultimate observational wall. Any event that occurred before this time, when the universe was still an opaque plasma, is fundamentally hidden from us. The light from such an event, including a hypothetical gamma-ray burst, would have been immediately absorbed and rescattered, its information lost forever in the primordial fog. It could never have traveled across the universe to reach our telescopes. This is what the redshift value of z equals 20 represents, a timestamp. It corresponds to a time just over 180 million years after the Big Bang, which is still well after the era of recombination. So why is this the practical limit for detecting objects like GRBs? The answer lies in what happened in that intervening period. While the universe was technically transparent after recombination, it wasn't yet a good place for making things we could see. The cosmos was filled with a thick, neutral hydrogen gas, often called the cosmic dark ages. Without any stars or galaxies to light it up, it was truly dark. More critically for detection, this neutral gas is extremely efficient at absorbing high-energy ultraviolet light, the very kind of radiation that is a hallmark of a GRB afterglow. This process is known as the Lyman alpha absorption. Neutral hydrogen atoms have a strong affinity for grabbing photons at a specific energy, the Lyman alpha transition. For a gamma-ray burst occurring during this era, its brilliant afterglow of ultraviolet light would have been almost completely devoured by this pervasive neutral hydrogen fog long before it could travel any meaningful distance. The universe, while no longer a plasma, was still effectively opaque to the specific light that carries the signature of these events. It would be like trying to see a lighthouse through the thickest, most dense fog imaginable. The beam is powerful, but the fog absorbs and scatters its light into uselessness before it can reach your eyes. Therefore, a gamma-ray burst occurring at a redshift higher than z equals 20 might have happened, but it would be utterly invisible to us. Its light would be either trapped in the primordial plasma or completely absorbed by the neutral hydrogen of the dark ages. This establishes a firm, theoretical ceiling for our observational capabilities. We can ponder the existence of such events in the very first moments of structure formation, but we will likely never observe one directly. The universe itself has drawn a final curtain, a limit imposed not by our technology, but by the fundamental physics of light and matter in the infant cosmos. This horizon reminds us that for all our power to look back in time, some chapters of the universe's history are forever closed to direct observation, existing only in the realm of theoretical prediction and our own awe-inspired imagination. And so we arrive at the final, most profound fact of all, the grand unifying idea that connects every astonishing detail we've explored. Gamma-ray bursts are the universe's most powerful time machines. This isn't a metaphor or a flight of fancy. It is the literal, functional reality of how these events are used in modern cosmology. Every time a satellite like Swift or Fermi detects a burst from a redshift of 6 or 8 or even higher, it hasn't just found an explosion in a distant part of space. It has intercepted a message that has been in transit for over 13 billion years, a data packet from the universe's infancy, encoded with the physical conditions of a reality we can never visit. We are not just looking far away, we are peering directly back into deep time, witnessing the violent death of a star that exploded before our own planet, our Sun, or even our Milky Way galaxy had even begun to form. This capability transforms these cataclysms from mere objects of study into active investigative tools. Think of a historian who only has textbooks written centuries after an event. Their understanding is based on second-hand accounts and interpretations. Now imagine that historian suddenly gains access to a sealed letter, written on the day of the event itself, preserving the original ink and paper, detailing the exact weather, the political climate, and the emotions of the people involved. That letter is a time capsule, and that is exactly what a high redshift gamma-ray burst is for cosmologists. Its light hasn't been filtered through billions of years of interpretation. It is a first-hand witness, carrying within its photons the raw, unedited data of the early cosmos. By analyzing the specific wavelengths of light absorbed by gases along its path, the cosmic barcode we discussed, scientists can perform a forensic chemical analysis on the universe when it was only a few 100 million years old. This direct observation is revolutionizing our understanding of the cosmic dawn. Before we could use GRBs in this way, the first billion years of the universe were largely theoretical, a blank canvas on which we painted models and simulations based on the older universe we could see. These bursts are now filling in that canvas with hard data. They have confirmed that massive stars did indeed form astonishingly early. They are helping us map the progress of reionization, showing us how and when the cosmic fog lifted. They are guiding our telescopes to the faint dwarf host galaxies that nurtured these first stars, galaxies that would be far too dim to find on their own. Each distant burst is a brilliant flashbulb going off in the dark, ancient universe, and in that momentary flash, we can see the structure of the room, the distribution of matter, the composition of the gas, the very architecture of the nascent cosmos. Ultimately, the study of these most distant events is about answering the most fundamental questions of our existence. How did the universe transition from a hot, formless soup of particles to the complex, structured expanse of galaxies, stars, and planets we see today? What were the first stars like, and how did their spectacular death seed the universe with the heavy elements necessary for life? By using gamma-ray bursts as our time machines, we are not merely satisfying scientific curiosity. We are reading our own origin story, written in the violent, beautiful language of stellar collapse and light. We are connecting the dots between the explosive death of a star at the edge of time and the atoms that form our very bodies. It is a humbling and awe-inspiring thought. In our quest to understand the universe's most distant and powerful explosions, we are, in the most profound way, discovering ourselves. So let's bring it all together. We've journeyed through 30 mind-expanding facts, from their discovery by Cold War satellites to their confirmation as black hole birth cries, from their fleeting visible light to their persistent multi-wavelength afterglows. We've seen how they act as cosmic lighthouses, their light stretched by the expanding universe into a redshift value that serves as a direct timestamp from the cosmic dawn. We've met record holders like GRB 090423, a stellar death that illuminated the universe when it was a mere 600 million years old, and marveled at events like the Clark event, so powerful it was briefly visible to the naked eye from 7.5 billion light-years away. We've explored their dual nature, long bursts heralding the death of massive, fast-spinning stars and short bursts signaling the final embrace of colliding neutron stars, a fact spectacularly confirmed by the multi-messenger astronomy of gravitational waves. We've delved into the terrifying physics of their relativistic jets, the energy of a sun's entire lifetime focused into a beam narrower than the space between your fingers, and confronted the chilling possibility of a nearby event, a silent threat to our planet's biosphere. We've considered how they might have sterilized nascent planetary systems in the early universe, potentially dictating the very schedule for when life could emerge. We've seen how they illuminate the epoch of reionization, acting as backlights to study the clearing of the cosmic fog, and how they point us toward the existence of mythical population 3 stars, the first pristine giants of the cosmos. We've uncovered the mystery of dark bursts, hidden behind veils of dust in stellar nurseries, and speculated about ultra-long events and pair instability supernova that could tear a star apart completely. We've looked to the future with observatories like Vera Rubin and James Webb ready to find thousands more, pushing our view back to the final horizon at redshift 20, the absolute limit of our observable universe. But beyond this incredible catalogue of facts lies a deeper, unifying truth. These are not merely random, faraway fireworks. Gamma-ray bursts are fundamental instruments in the orchestra of cosmology. They are our most powerful time machines, providing core samples of the early universe that allow us to chemically analyze the gas between galaxies billions of years ago. They are standardizable candles, helping us measure the expansion history of the cosmos and probe the mysterious nature of dark energy. They are signposts to the faintest, earliest galaxies, which would otherwise remain invisible to our telescopes. And perhaps most profoundly, they are the direct link between the violent deaths of the first stars and our own existence. The heavy elements forged in their explosions and in the neutron star mergers that cause short bursts, the gold, the platinum, the uranium, were eventually incorporated into new generations of stars and planets. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were cooked in the hearts of stars that lived and died long before our sun was born. In a very real, physical sense, we are the legacy of these cosmic cataclysms. By studying the most distant gamma-ray bursts, we are not just exploring the edge of space and time. We are reading the story of our own origins, written in the violent, beautiful, and ultimately creative language of the universe itself. From the unimaginable power of a star's final breath to the faint whispers of light that have traveled since the dawn of time, these 30 facts are just the beginning of the story. The universe is a boundless frontier of mystery, and every discovery peels back another layer, revealing even more profound questions waiting to be answered. I want to hear which of these facts completely rewired your brain. Was it the concept of a gamma-ray burst as a cosmic time machine, the terrifying possibility of a nearby event, or the incredible link to gravitational waves? Let me know in the comments below. I read every single one. If this journey across space and time gave you a new sense of wonder, definitely give this video a like. It lets me know you enjoy these deep dives into the cosmos. And if you haven't already, subscribe to the channel and hit that bell so you won't miss our next adventure. We're just getting started exploring the greatest mysteries of the universe, from the enigmatic nature of dark matter to the search for life beyond our solar system. Thank you for watching, for wondering, and for sharing in the awe that only the cosmos can inspire. Never stop looking.